Hello. Happy Friday. Good afternoon. Hope you're all doing well. I'm excited to be here. I'm Ethan. I go by Ethan Gunderson on most things online. I do Elixir and infrastructure things at cars. I'm a weird coffee person. I go through extreme lengths to get a good cup of coffee or espresso, which I guess could have been my weird fact, now that I think about it. Or fun fact. Yep, that's a bummer. All right, and I love triaging incidents. And truly I do, there's really nothing more exciting than running into a problem that breaks my mental model of how the system should work. So whenever I say that's not possible, that shouldn't be happening, it means my mental model was wrong, and now I get to correct it by triaging this incident. I think that's really cool. A side effect of this trait is I'm often on call. I think at this point in my career, I've been on call more often than not. Who here is on call regularly for a production system? Yeah. Is anyone on call right now? Yeah, all right, wow. Bravo, that's impressive. So you'll know what I'm getting at here is whenever we have to maintain a production system, whenever we have to take care of it, grow it, we deal with a lot of misfortune. At any given time in any production system, there is some amount of misfortune that's going on. Unexpected latency, a server completely dies, unexpected user input, just terrible things are happening on every server, basically all the time. And so really the question becomes, how do we detect it? How do we know when our code is working as we expect? So that's what we're going to talk about today. So today's agenda, I'm going to go over telemetry, what it is, how it works, how we can use that to build up an instrumentation system for an application, how we can do some metrics collection, some gotchas, and some final takeaways. So first, let's back up a little bit onto the Cars relaunch of Elixir. So Cars connects people who sell cars with people who wants to buy cars. And as of June of last year, we are now an Elixir shop. We rewrote everything that was in place onto a majestic monolith umbrella application. And we did something that most people would probably say is not a great idea. We did a big bang rewrite. We went from roughly 0% of traffic to 100% of traffic in one day on a language we had no production experience with, on a runtime we had no production experience with. In other words, we were inviting misfortune. Things would probably not go right, and we needed to account for that. So we knew this going into it, and so we set out to build an instrumentation system that would help us avoid that misfortune or detect that misfortune. So some design goals we had. We wanted default instrumentation. So if any given feature developer, product developer did nothing, they would get some level of instrumentation. They would be able to detect if their code was working roughly how they would expect. We wanted them to fall into that pit of success. We wanted to cover both application traces or application instrumentation. So a person visits the website, a background job fires, that kind of stuff. We also needed to cover the VM. So how is the beam actually running? What's our memory look like? What's our scheduler utilization look like? And it needed to be extensible. We didn't know what we didn't know, so we knew that we would, over time, develop or uncover things that we would also need to instrument. We would have to build upon this. These aren't new concepts by any means, but it's what we set out to do. We had some false starts at first. We could instrument some things. We can get some VM memory level stuff, but it wasn't really extensible. So after going through that, we finally landed on using telemetry as the basis for everything that we do. So what is telemetry? According to the docs, it's a library for dynamic dispatching of events. So really what telemetry is going to do for us is it allows one piece of code to emit events to another. It allows it to announce that something happened. In order to do this, we get a couple of functions that we can do. So we can attach ourselves to an event name. So we can give it a unique ID, the event name, and then a function to call when that event is triggered. So over time, as different things attach to events, we build up this list of things, right? And then at some point, the thing that wants to do the announcement is going to call an execute. And then at that point, telemetry will go through and walk our list. Well, every handler that's registered to that event name will get fired one by one. And yeah, so there's some design constraints to the system, right? Handlers are processed sequentially and in the same process. It's not like a pub sub or anything like that. It can be kind of surprising. I think when you first look at it, you might assume that there's maybe multiple processes or things happening in parallel. That's not happening. And handlers that throw an exception are removed. Telemetry calls this detach. You get a nice little Erlang error, and that handler will never be invoked again without some manual intervention, right? So to highlight how this is useful, let's go through some code that's written without telemetry. So this is some code / pseudocode. We're going to create a user. Based off the success of that, we're going to log some data, and then we're going to either show or redirect, right? This is pretty typical, but we're already mixing concerns here, right? We have business logic and we have instrumentation logic, and they're conflated here. And so imagine when this grows. Often you'll want to do things, a multitude of things. You want to have some logs, some metrics, maybe of analytics. You probably have exception tracking somewhere. So really quickly, this code becomes overloaded with instrumentation logic when it should be focused on application logic, the business domain for the problem it's trying to solve. So how can telemetry help us with this? With telemetry, all this code needs to do is say what happened. So the success, user creation success, or exception, you can give the exception event, and we can pass some metadata around. And then on somewhere else in our code, we can attach ourselves to that event. We can say things like, when the user creation success happens, I'm going to log this message. When it fails, I'm going to also log. But then we can have a totally separate one that also attaches to the exception event and invokes our exception handling code. It's cool. We've separated concerns now. This code's easier to test because everything's only responsible for one thing. The application logic, when you actually go to look at it, you can clearly see what it's doing instead of having to muddle through all the instrumentation code that was there. And this concept is actually called domain probes. So this isn't new. And yeah, so this is really just, let's encapsulate the domains of the things that we're dealing with. We can have clearing separation between application logic and instrumentation logic. So that's cool. But really, telemetry's utility comes when libraries can emit events to application code. So I think a good way to highlight how this is useful is to talk through a library that does not use telemetry. And for that, I'm going to talk about Hackney Metrics. So this is not a knock against Hackney at all. We use it extensively. This is merely just I'm going to highlight and contrast the differences of the metric system. So Hackney Metrics requires you to do two things. First, you need to define some module that implements some protocol for all of the events or all the functions that Hackney will call as part of its metric submission. So there's update, increment, another update. There's about 17 of these. And then you have to tell Hackney about this module. You have to, And then in the Hackney code itself, it's going to directly call those functions that we've set up. So there are some downsides to this approach, right? There's a one-to-one mapping of metrics handling. What if we want to do more, right? Hackney has one slot for the module, and we've occupied it with the module we just threw in. So if we want to start, for lack of a better word, if we want to start dispatching to more things, we have to now implement the dispatching ourselves. That's kind of unfortunate. What if we don't care about all those metrics? Maybe we only care about one of them. Now we have to implement the entire protocol and essentially just no-op the rest. And what if our module fails? If our metric module throws an exception, in this case, Hackney will fail the request. And that's a pretty awful scenario to be in, where your instrumentation logic itself is causing failure upstream. So what would this look like if we ported it to telemetry? So the Hackney code would emit an event. That's it. It would do this wherever it needs to. It would include the metadata and the measurements that it cares about. Or not that it cares about, sorry, that it would like to inform the application code about. And then somewhere else, we can attach ourselves to that event and do what we wish with it. So the benefits here, the library, in this case Hackney, needs no configuration. We don't have to tell it at all about what we're doing. The application can subscribe to only what it needs. And the really big benefit here is that we can get consistent. Every library no longer needs to implement its own callback system, its own metric system. It can use telemetry. That means when we go to consume those events, we can go read the docs on what's being emitted, and that's it. Like it's no extra code, no hurt feelings. It's just exactly what we need. So that's it. That's telemetry. So let's start by taking telemetry and building on top of it. How can we get from this system to something that can help us determine how our requests are doing? So for that, let's introduce a noun, traces. So what's a trace? A trace is a measurement of the entire execution of a request. And this is a really broad definition, and that's intentional. A request can be whatever you need it to be. We're a website, so in a lot of cases that's going to be a web request. It's going to be we'll want to span the entire request response lifecycle. We also have a lot of background work. So every background job that gets processed, we consider a trace as well that we'll want to instrument. So how do we do this? So as an example, and luckily Phoenix has a slew of telemetry events that it emits. One of those is Phoenix endpoint start. So when the endpoint gets the request in, it will emit this event, and then we can start our trace by attaching ourselves to it. Likewise, it has a stop. So we can stop our trace there. So if you notice, like I did a little hand wavy there. The function bodies were just comments of, start trace. We have to fill that in with something, right? So we're a spandex shop. We're a Datadog shop. So spandex is basically a purpose-built library for sending and managing trace data and sending it to Datadog. That being said, there's other tools out there, both paid products and open source products. So there is another library called OpenTelemetry, which does something very similar, but it's vendor agnostic. So you can send it to a slew of different places, all with the same API, all the same interface. The examples I'm going to give are going to be in spandex because that's what we use and that's what I'm familiar with. But by and large, they should be roughly interchangeable. The community at large is mostly going towards OpenTelemetry. So if you are interested in setting this up, I would investigate that. So with that in place, we have something that looks like this. We've sent the measurement data to our tool of choice, and it will display us a flame graph. So now we get a lot of stuff out of this. We can see how long the trace took. We can see if it errored or not. And that alone is pretty useful. Right? We can monitor changes over time. You can monitor trend lines. And we kind of roughly get this for free. So we've already kind of got that default level of instrumentation. Every request coming in to Phoenix will generate this trace, regardless of developers doing any manual work. But we can do better, right? So for that, we're going to add another concept called spans. A span is just a unit of work inside of a trace. Again, broad definition because it can be what you need it to be. So a couple examples. Often it's useful to consider your function calls a span. It's a unit of work that you're doing. We can decorate those with spans, like the span decorator tag. Or maybe it's more useful, like if you're iterating over a collection and you want the work that you're doing in there to represent a span. Like you can be flexible and define that how you want. But now we have something that looks like this. This gets neat as well. So we know how long the trace took, but now we can see, what's the longest part of this request? If we were asked to improve the performance of this, we can go and look and see is there low-hanging fruit? Like what is actually taking the time? What is this composed of? We can go further. So we can do things with telemetry, in this case, Ecto. So Ecto will emit a telemetry event for every query that finishes in the system. We can attach ourselves to that event and start a trace. So then now we know all the database calls that happen in the system. So really quickly, we can start to see like where we're spending time in a request. When misfortune happens to us, we can see if it's related to a subsystem or is it general latency. Yeah, but we can do better. For that, we're going to need tags. So tags are a way to find commonalities between traces. We can use them to filter and aggregate. It also allows us to add context. And so this is the context that you really want when you're triaging an incident, right? You want to know this function was called with these arguments, or this was the state of the feature flag that was set, or you name it. Like this is where you can get really rich in the data that you expose. So we have a couple different ways we can do this. We can add tags on the decorator level, or in the functions themselves, we can update our spans with tags. So in this case, we now know that this request function, when it finishes, we know the status code and the URL that we called. And it goes further. So going back to the Ecto example, we get a bunch of really rich information out of Ecto. We know the query that was executed, we know the operation, we know how long the query time took, how long it took us to decode. And so then we can use that to build this. So now we can look and see this, this request performed in this rate, and we can look into why. Like, our HV call took a really long time, but it 200'd, all right? Or, in this case, we dropped our entire database. So I'm gonna pause for a little bit to feel like I went over that a little fast and didn't highlight how cool this is. So we have instrumentation for every query through our system, regardless of where it happens. We know how long it took. We know the query itself. We have this incredibly rich set of data. That means something goes wrong. I can go and look and see did all of the database queries change? Are we having a database problem? Did one of them change? Are we seeing latency in one? Did we miss an index? Is this a new query because I'm just now seeing it? It opens up a ton of options. Actually, I can't stress how nice it is to have that quantity of data when you're under the gun to try to figure out what's going on. And we did it with no developer involvement. Developer adding a new query, it's automatically going to show up. They don't have to do anything, but they get the benefit of it. By just consuming one telemetry event. That's it. So now, and that was just with Ecto. Expand that to all the other libraries that you use. Expand that to HP calls. Expand that to, we talked about Phoenix, but there's Cowboy. There's a ton of opportunity here to automatically gather really rich data. But we can do better. For that, let's talk about distributed tracing. So this is, again, like a relatively simple concept. We have traces that are somehow related, and so we want to tie them together when we visualize them. This would be really evident in a system that's like a services architecture. Right? You have a request that comes in. It could take potentially multiple services to satisfy that request. And while each of them individually is useful, it's really useful to see the totality of what it took to satisfy that request. But it's also useful for things like background jobs. So we use Oban as one of our job frameworks. And so with it, we can start doing things like we can inject trace context and trace metadata before we insert the job. And then when we get the telemetry event from Oban, we can inspect it and see if there's trace context, we can continue the trace, and if not, we can start a new trace. And so then we get cool things like this. So now, not only can we see the initial user request that came in, but if there's side effects happening via asynchronous jobs, we can also see that. So now we can see not just the request response, but the impact of that request across the entire platform, which is very useful. So let's revisit our design goals a bit. We've achieved default instrumentation. We can get a lot without doing a little, or with doing a little, the inverse of that. And it's extensible, right? So we can continually add on new telemetry handlers. Like every time you onboard a library, we can go and look and see, does this thing expose events that can help us either enrich other spans or create new spans around. But what's left is like the VM metrics part, right? There's a bunch of stuff that happens in the system that is not directly related to a user request. Long-running processes, just the general health of your Beam VM. So to take care of that, we need to talk about a few more things. Telemetry metrics, pollers, and reporters. Telemetry metrics are just a way to define metrics based off of events. So this will be a little bit more obvious when I give an example. So in this case, we're going to take the Hackney update histogram event, and we're going to execute a telemetry event. I bet you can't tell what code I've been working on lately. And then we can define metrics based off of it. So telemetry metrics will automatically concatenate measurements on event names. So since we are looking for the connect time and response time measurement, we know that we can build a distribution off of that, and we can tag it with our host. So now we can take a look and see what is the average connect time or response time to any third-party host that is going through Hackney system. In order to collect those measurements, we need, oh, that just works, sorry. For other things, like for things that we want to periodically check, like CPU usage, schedule utilization, we have telemetry poller, which is essentially just, we're going to execute a whole bunch of telemetry events on a cron. We'll inspect the things that we need to inspect, and then just emit the event off of it. And then we can define our metrics. So in this case, we're grabbing everything I could probably think of that would be interesting when triaging. So we run these every 15 seconds, every 20 seconds, and we can build a picture of CPU use over time, atom use over time, that level of stuff. And then reporters. So far, we've only really defined a way to collect data. We also need a way to transmit it. That's where reporters come in. They are responsible for receiving telemetry metrics and translating them to the system that you're going to send them to. So that could be wherever you want. There are open source reporters for Statsd and Prometheus, which I'm guessing would cover most people. So that means that for anything that we want to track over time, we really only need to figure out two things. We need to figure out a function that can gather the data that we care about, and then we just need to define the metrics based off of it. So this entire problem becomes, how do I measure the thing that I care about, not the mechanics of how I'm going to send data around. So that becomes a fairly easy process, and also satisfies our last design goal. So in order to wrap all this up, we have a part of our umbrella is an application called Meter. It's our deployment agnostic tracing, spanning, tagging metrics application. It cares a whole lot about telemetry and observability and everything around it, so the other parts of the system don't have to. And it looks something like this. So this is the thing, all the attach calls that I had in slides would live in here. This is going to attach to everything that we care about with every library that we use. It's going to define all the pollers that we care about. It defines all the metrics we want to gather. And it's wrapped up in one umbrella application so that when we do releases, so we deploy, we're like a mono repo deploy to services kind of. When we have releases that go out, it will include this so that it gets all of the instrumentation that it needs. Like really, this is our force multiplier. So as we spin up new Elixir applications, new Elixir projects, we can drop Meter into it and get all the benefit of the instrumentation that we already have, which I think is really important. This type of work is usually underfunded. You're always going to have significantly more people caring about the product that you're building than how to instrument stuff like this. So finding ways to leverage this work is important. Let's talk about some gotchas. I always like talks like this when the person like highlights this thing and talks about how great it is, but you always want to hear like from the disgruntled coworker of like, here's all the things that aren't working. Like who's like back in the office right now taking care of the stuff that I'm not talking about. So I'm gonna cover all that right now. So the first gotcha, this is a terribly leaky abstraction. So on the surface of it, we're dealing with telemetry. And then almost immediately you have to know what spandex is in order to get access to spans and tags. And at that point, you're gonna figure out where spandex comes from, and that's meter. So now you have to know kind of what meter is. We, and when I say we, I actually mean me, I have done a terrible job of writing abstractions around this kind of stuff. So we leak these implementation details quite a bit. Traces can be lost. So there's no checkpointing in the system. You start a trace, you add trace context with spans and tags, and then at some point you call stop trace. What happens if that stop trace is never called? Like when Kubernetes ooms your VM, or there's some other catastrophic failure. You lose all of the open traces that were present in that VM at arguably the worst possible moment, because that you're gonna wanna know what was happening on that when it failed. Traces can be completely missed. So we rely pretty heavily on the Phoenix endpoint telemetry events to start traces, but there's a whole mess of networking that happens before that's invoked. We have load balancers, we have CDNs, we have the clients themselves. So really, until you get distributed tracing all the way down the stack, so you're starting a trace on your client, on the browser, you're gonna have the opportunity to miss traces. And this one's real fun. Tracing across a process boundary can be really difficult. So to like talk through this, I have a little diagram. So inside of every Erlang process is this thing called the process dictionary. It's this neat little thing we don't talk a whole lot about, but it's this piece of mutable state. And this is where spandex and OpenTelemetry keep trace data. So when you call OpenTrace, it's gonna put some stuff in here. When you add spans, it's gonna put some stuff in here. And that's all relevant to the process that is being executed right now. But what happens when you spawn a new process? You spawn a new process, and that child process adds some data. That's gonna go into a different process dictionary. Then that process is gonna finish, and eventually this one will finish. So this one will close its trace, but it won't have any context of what happened in its children processes. All that's lost. You lose all that fidelity. So there are some ways to work around this. You can pass trace context around. So if you know you're gonna start up some stuff, you're gonna start a task, or you're gonna do some gen server work, you can pass an existing trace context and do a continue trace. You're effectively doing a mini distributed trace. This doesn't always work though. Some libraries will open or start new processes for you and not expose that in a way where you can inject data. It's like small fun story. I gave this talk twice as practice. Both times when I was done, I had Slack messages waiting for me where someone was wondering why they were missing span or tag data. This was the root cause for both of them. So fair to say we run into this frequently. All right, some takeaways. At some point, one way or another, when you run a production system, we will experience misfortune. And I think it's our job and it's our responsibility to account for that. Telemetry is super neat. I think it's a really powerful library, and as more libraries adopt it, the more powerful it gets. Observability, it's kind of a hot word, contested word, but for me, it's about being able to answer the questions that I didn't know that I had. We get there by adding as wide of traces as possible, as rich with data as we can get. That means constantly looking for new things to span, constantly looking for new attributes to add, new tags. We're not there yet, but we're getting there. And we've had to build very little to get this. There's almost no code in this talk because there's basically no code to write. We're gluing things together that the community has already built. And I think that's really cool. I'm really excited for the direction that that's heading. Yeah. So if this type of thing is interesting at scale, Cars is hiring, I'd love to talk to you. Thank you.